Hello friends. So we have been considering some of the basic aspect of vector calculus. So in our previous lecture we considered dot and cross products between two vectors. Now in this lecture we will build on it, and we will see other numerical operators that are relevant to our materials research. Now we will begin with the Fick's first law. So if you are from a materials background, a metallurgical background, chances are that you are already familiar with the Fick's first law. So what Fick's first law states is, if you have a gradient in concentration, so there it uses the term gradient. So if you have a gradient in concentration, there is a flux that is induced. So the Fick's first law, it introduces, or it talks about two critical aspects. One is, it talks about a condition where there is a gradient in concentration, and if this condition is satisfied, then a flux is being introduced. So we need to understand what gradient is in order for us to understand how the flux is induced. Now generally when we consider a system with a specific concentration, it is possible for us to consider two types of system. One is a homogeneous system, wherein at every point the concentration remains the same. So when you consider, say, a binary system, say a plain carbon steel with iron and carbon, it is possible for us to consider a homogeneous system wherein the concentration at every point is the same. So the concentration is rather independent of the points that we consider in this system. On the other hand, it is possible for us to consider a heterogeneous system wherein, depending on which point you consider, the concentration of carbon varies. So we are considering a binary system, a steel. Now there are two ways we can consider it. One is an homogeneous system wherein at each point the concentration of the carbon remains the same. There is also another possibility where, depending on the point, say for instance in this case x1, y1, so if you consider the system in the coordinate system of x and y, so this is x, this is y, it is possible for us to consider such a system an heterogeneous system wherein, which is characterized by a difference in the concentration based on the point that you consider. So the concentration at x and x1, y1 would be different from the concentration at x2, y2. Now this heterogeneous concentration, or in this heterogeneous system, the concentration is essentially dependent on the position that is described by x and y. Now when the concentration depends on the position means the point in the space, then what essentially we have is, when you move along the space, there is a change in the concentration that we observe. So when you have a heterogeneous system and the concentration at each point varies, and when you move along the space there is a variation in the concentration, then in this system what happens is, or what Fick's law states is, in this system there will be a flux that is introduced, a flux that will be introduced in an heterogeneous system, and this flux is governed by the gradient. So what essentially we mean is, according to the Fick's law, when you have an heterogeneous system, there is a flux that is introduced. So when you don't consider, don't want to consider the mathematical aspect or what a gradient is, when you consider conceptually what Fick's law, for the Fick's first law states, what Fick's first law states is, when you have an heterogeneous system, that is, when you have a system wherein the concentration of the system varies with the space, varies with the position, then in such a system flux will be introduced. This is the Fick's law. Now this is just the generalized understanding, or just a conceptual understanding of Fick's law. Now when you want to derive an expression, when you want to represent this Fick's law, the Fick's first law, in the form of an expression, then you need to understand what a gradient is. Now the gradient will be helpful to us when you want to mathematically express what the Fick's first law is. One way of conceptually treating is heterogeneous system, difference in concentration with respect to space, there will be a flux that is introduced. So that will be purely a conceptual understanding of what a Fick's law is. When you want to have a numerical expression for it, then you need to understand what a gradient is. So that is essentially what we will try to understand. Now when we have a concentration that is dependent on the spatial position. It is possible for us to represent it in a three-dimensional manner. So what you can do is, we have represented in this two-dimensional system each point in terms of x and y. So we have represented x1, y1 as a point, x2, y2 as another point. Now in this heterogeneous system, the concentration at one point is different from the concentration at other point. Now this can be represented in a three-dimensional manner when you have your x in this direction, y in this direction, and you have your concentration in this direction. So supposing, so this concentration is again dependent on x and y. Supposing at this point x1, y1, if your concentration is the highest, then the concentration will be here. And if at a point x2, y2, say at a point x2, y2, say it's here, you can estimate the corresponding concentration from the system, and the point will correspond to this here. So what essentially we can do is, we can build a plane in this three-dimensional system that essentially represents how the concentration is distributed in the system. So what we have is, we have an actual system, and in this actual system what we essentially have is, in this actual system it is an heterogeneous system, and depending on the points that you consider, there is a difference in the concentration. Now what we have done is, since this is a two-dimensional system, we have represented, or we have considered a three-dimensional axis. Two of the axes help us describe the points that we are considering. So this point here is x1, y1, and this point here is x2, y2. The 2 points that we have considered. It's just this x and y axis, it helps us include the points we are considering. And now in the third axis, we consider the corresponding concentration, and therefore we are able to build such a surface, such a two-dimensional surface in this three-dimensional region. So essentially what we have created is, we have created a two-dimensional surface to represent the distribution of concentration here. Now this surface is described by this function here. So this function is dependent on x and y. So x and y are the spatial coordinates. So x and y in this case are referred to as the spatial coordinates. The reason we refer to this as spatial coordinates is because they help us describe the space that we are considering, the system that we are considering. So this x and y are referred to as the spatial coordinate. Now since the concentration is dependent on x and y, it is possible for us to consider what would be the change in this concentration if we consider just the x-axis of our spatial coordinates, and separately we consider the y-axis of our spatial coordinate. Let me repeat. Now we have a concentration that is dependent on spatial coordinate. It means when you move to different points, the concentration is correspondingly going to vary. Now how it varies is possible for us to understand, because we have seen what is the meaning of derivative is. So we have seen that the derivative is nothing but the rate of change of a function with respect to a variable. So now I have a function. Of course this function is dependent on two different variables. Now when I consider the derivative of this function with respect to a specific variable, then what essentially I know is how this concentration changes with respect to that variable. So I have a function. So I know how the concentration is distributed in the space of x and y. Now I want to know how the concentration is going to change when I move along this x direction. So, and also I also want to know how the concentration is going to change when I move along this y direction. So I am starting here. I want to know if I move along this direction, how is my concentration going to change? If I move along this direction, how my concentration is going to change? This is something that I want to know in order to describe the concentration distribution. So that can be understood if I take the partial derivative of my concentration with respect to one of the axes and sum it up with the partial derivative of my concentration with respect to the other axis. So what essentially I have done is, I have a concentration function. This is possible because I am considering a heterogeneous system. In the heterogeneous system, the concentration varies with the spatial points, and in order to describe these points, we introduce a spatial coordinates, and I want to know how this concentration varies when I move along these different spatial coordinates. So therefore I end up with this expression here. Now since we have considered just the dimensional representation, the system that originally we have considered as 2-dimension, we just have x and y axis. Supposing if I have a 3-dimensional system, and in that 3-dimensional system, in the real life 3-dimensional system, I again have an heterogeneous condition and impose an heterogeneous condition, meaning in all the x, y and z axis, there is a change in the concentration. How the concentration varies can be expressed as this, the partial derivative of the concentration, which is now dependent on x, y and z. It is no longer dependent on x and y alone. Now I'm extending my condition to a 3-dimensional one. Now in this case, the corresponding expression that helps me in understanding how my concentration changes with respect to the spatial coordinates will be of this form here. So if I have a definite expression, that is dependent on x, y and z, then I will be able to substitute this expression here and find the partial derivative of it with respect to x, with respect to y and with respect to z, and sum it all up. So once I sum it all up, if it is still dependent on x, y and z, so this is an expression, and this expression let us refer to as d of, let us just refer to it as d, and so this d, what it essentially considers is the partial derivative of c, how the concentration changes with respect to x, how the concentration changes with respect to y, how the concentration changes with respect to z, and sums it all up. Now this d, after summing it all up, if it assumes, if it is still dependent on x, y and z, so if this could be the case, this could be the case when it reflects, when it is the nature of your distribution. So your distribution, your concentration is distributed in such a way that after taking the partial derivative, still this function is dependent on x, y and z. Then if I substitute, say for instance, if I consider a specific point x1, y1 and z1, if I substitute those values, then I would know how my concentration is going to change. So with respect to this point, I would know how my concentration is going to change. So what is the slope at this point is something that I would know when from this expression here. So what essentially I have done is, I have a function of concentration in a heterogeneous system. I have a heterogeneous system, concentration is varying at different points. Now this variation in the concentration at different points, I have rather expressed it in the form of a function. So the heterogeneous distribution, I have expressed it in the form of a function, a 3-dimensional function that is expressed as c, that is of x, y and z. So x, y and z is the independent variable. Depending on my position, my concentration varies. So as a function, I have represented the heterogeneous 3-dimensional system. So of course, when you consider a molten state of say steel, it comprises of iron and carbon, there is often a fluctuation locally in the system. So the carbon concentration is not constant all over, there is a fluctuation locally within the system. And if you are able to quantify that fluctuation, then what essentially we have is an heterogeneous system. Now what you have developed it, you have represented this heterogeneous system in the form of a function here, and you need to know what is the slope of the function, how this function is varying with respect to the spatial position, and therefore you have considered the slope of the function with respect to individual axis. And supposing if the function is still dependent on x, y and z, then when you substitute the corresponding points, when you consider a specific point, substitute the value of x and y in that point, then you will be able to understand how this particular heterogeneous concentration is varying at that specific point. Now, in some mathematical lectures, some mathematical textbooks, this expression here, this derivative here is referred to as the directional derivative. So what directional derivative essentially states is, this directional derivative with respect to a point, it states how your function is varying. So what is the slope of your function? Essentially, this is what we see, the first derivative with respect to one of the variable. So the directional derivative states what is the slope of the variable with when you consider a function and it is with respect to a given point. So what essentially you have done is, you have considered the partial derivative of a spatially varying function with respect to the individual coordinates that describe that specific space. Now ultimately, for a point, when you have such an expression, when you have such a function that includes all the partial derivative, and when you substitute the corresponding values that coincide with a point, then ultimately you would end up with a scalar value. So the directional derivative will be a scalar value that talks about a slope at a given point for a heterogeneous system. So in this case, you have a function varying with the spatial position, And when you consider the directional derivative at a point, it gives us what is the slope at that specific point. So at x1, y1 and z1, what is the slope of this function is being offered by, or it is being estimated through the directional derivative. Now, when we include a vector notation to this directional derivative, for instance, while estimating the partial derivative of this function with respect to x and with respect to y and with respect to z, you are introducing rather a vector notation to it. You are rather coupling the derivative of the function with respect to x to the I vector and the derivative, the partial derivative of the function with respect to y to the j vector, and the partial derivative of the function with respect to z to the k vector, to these orthonormal bases, then this function, this operation is referred to as the gradient. So what essentially we have is, the gradient is rather a factorial representation, one way of looking at it, rather not so accurate way, but when you consider the flow of thought, in this case, one way of looking at it is the factorial representation of the directional derivative. So in some max textbook, this is how the gradient itself is being introduced. So what essentially we then have is, we are finding the slope of a function, in this case the concentration, which is varying in the different position, which varies with the spatial position. So what essentially we are doing is, we are finding what is the slope of this function. So we have a system, a three-dimensional system, and in this three-dimensional system, depending on your position, the concentration is varying. So in order to express this concentration that is varying with respect to position, you represent it in the form of a function, and this function is dependent on these coordinate axes x, y and z, the spatial coordinates x, y and z. You take the partial derivative with respect to x, y and z and sum it up, you end up with the directional derivative. Then to that you add a vector notation, you end up with gradient. Now when you just focus on, without considering the vector aspect, when you just focus on the magnitude of the individual terms of the gradient. So what it essentially means is, this partial derivative of c with respect to partial derivative of x, what it essentially means is, it considers the concentration along the x direction. So you have your point c0, you have your point c1 rather, or you have your point x0, you have your point x1. So the gradient term here, the first term, the magnitude term of the first term of gradient, that is this term here, when you consider the magnitude term alone, that is the partial derivative of c with respect to x, what it essentially considers is, along the x-axis it considers 2 points, and it considers the concentration at x0, c0 and c1, and the partial derivative is nothing but c1 minus c0 by delta x, where delta x is x1 minus x0. So this is what the first term is. So this is what the first term is. The same can be extended for the second term. So the gradient term here, so or the magnitude of this gradient term is nothing but how the concentration varies in a specific direction, in the x-axis, in the y-axis and in the z-axis. That is what the magnitude here considers. Now what Fick's first law states is, we have a gradient, and this gradient is what introduces the flux. So we have a gradient represented, we can write it as grad, and this grad, it introduces flux, and this flux, the amount of flux is proportional to negative of this grad. This is what the Fick's first law states. So the Fick's first law states that there will be a flux that is introduced, and this flux will be proportional to the negative of the gradient of the concentration. So now when your concentration is homogeneous, when your concentration is homogeneous, then what it would essentially means is that the concentration is no longer dependent on x, y and z. So let me repeat, when your concentration, your system is homogeneous, your concentration is no longer dependent on x, y and z. So what it means is, this partial derivatives that rather estimates the magnitude along each of the orthonormal bases, here the numerator c1 and c0 in a homogeneous system will be equal, that is c1 will be equal to C naught. So therefore the magnitude itself, it turns to 0 in a homogeneous system. So therefore what essentially would happen is the entire grad of C, the gradient of C, will turn to 0. So essentially there will be no flux that is introduced into the system. So conceptually we have this understanding that when we have a homogeneous system there will be no flux. When we have an heterogeneous system there will be flux. That is what conceptually the Fick's law states. Now why there won't be any flux when you have an homogeneous system is rather it is possible for us to understand when we consider the mathematical aspect of it. So when you consider the mathematical aspect of it, this is how the gradient is expressed. So the gradient of C, this is how it is expressed. And the magnitude component of this gradient of C is rather expressed in this manner, again from the first principle estimations. And now when an homogeneous system, since this difference turns to 0 because as you vary in the spatial positions, the concentration is going to remain the same, all the magnitude turns to 0 and ultimately the gradient of 0, so there will be any flux. However, we see that when you have an heterogeneous system and when the C1 is not equal to C0, then you will have a non-zero entity. The magnitude of this partial derivative will be non-zero. So this essentially means that there will be a flux that is introduced. So let me repeat, when you have a system that is homogeneous, the magnitude of the gradient turns 0, therefore there will be no flux. So that is what the Fick's first law state. However, when it is non-zero, when your system is heterogeneous, so the concentration is dependent on the position, then essentially the magnitude of your gradient will be non-zero. So ultimately there will be, so this term on the left or the right would be a non-zero, so there will be a flux that is introduced. So this is a mathematical perspective of the Fick's first law. Now it is rather quite important for us to understand that this negative sign here is rather coupled with the Fick's first law. The negative sign, we cannot have the Fick's first law without the negative sign here. So what does this negative sign indicate? Now when you consider, so we have considered homogeneous system wherein C1 is equal to C2. So when you consider this homogeneous system, there is no flux. However, when you consider a heterogeneous system wherein C1 and C0 are not equal, they are different, then there is a flux that is introduced. So when you consider such an inequality, there are two possible inequalities. Either C1 can be greater than C0 or C0 can be greater than C1. Now, what essentially then we have is, if we take this case here, C0 that is greater than C1, then when you consider the partial derivative of the C with respect to x, in this case we have C1 minus C0 by delta x. So I have just written down what I have written here. But for in this case, since C1 is less than that of C0, what essentially we have is this will lead to a negative value. In the same way, if you substitute here, when you find the derivative for this case, the partial derivative for this case, it will be C1 minus C0 delta x. This will be positive. Now, when you consider the Fick's law and when you consider a system of this sort, we are just considering x-axis and we are considering the concentration along the x-axis. When you have such a distribution, so what we have is, so if we consider this point as x0 and this point would be then c0 and this point here as x1 and the corresponding concentration will be c1. So what essentially we have is, we have a c1 that is greater than that of c0. Now the Fick's first law, it comes with a negative sign associated with it. Now this term, this gradient term, when this condition is satisfied, this term will in itself be a negative term. So therefore, for the condition C0 less than or C0 greater than C1, what essentially then we would have is, we would have a positive flux. So let me repeat, when we have a condition that is C0 is greater than C1, we will have a negative partial derivative. And since Fick's first law comes with a negative sign here, so the negative gets cancelled out and ultimately you have a positive flux. Now if I want to represent what a positive flux would be, then in this case what we have is, we have represented rather in a reverse manner. So instead of this being our x0, let us, if we assume that this to be our x1, and this to be our x0, and correspondingly this will be our c0 and this will be our c1. So what we have is c0 is greater than c1. Then we have a positive flux. That means the flux will flow in this direction. There will be a flux that will move from the higher concentration to that of the lower concentration. So what Fick's law states that it talks about a flux that moves from an higher concentration to that of the lower concentration, and that is only possible when your C1, or rather in this case when your C0 is greater than that of your C1. So Fick's first law, it talks about the flux that occurs from a higher concentration region to that of the lower concentration region. Now, when you have a higher concentration and a lower concentration region, when you consider the partial derivative of it, like we have seen here, it will be a negative value. But we need to have a positive flux that flows from the higher concentration region to that of the lower concentration region. So when the flux is positive, what essentially we have is we have a flow from the region of higher concentration to that of the lower concentration. So that is what we physically observe. So in order to ensure that we are able to capture this positive flux from the region of higher concentration to that of the region of lower concentration, this negative sign is included. So now when you couple this negative sign with the negative sign which it generates from the partial derivative, then ultimately we end up having a positive flux. So by convention we have a positive flux when the flux moves from the region of higher concentration to that of the lower concentration. That positive flux is possible only when you include this negative sign here, and the gradient comes up with its own negative sign, and therefore we have such a flux here. Now when you consider this term, this here, that is this T is the reverse of this condition, then what essentially we have is we will have similar flux, but our consideration, the convention that we adopt would reverse. So therefore, even though it quantifies itself as a negative flux, the direction of it would still remain the same. So when you reverse, when you consider this condition of C1 being greater than, when you consider C1 being greater here, and when you consider the C0 this way, when compared to this direction, the flux now will be in this direction, because the C0 now, so or the C1 will now have a greater concentration when compared to that of the C0. So in that case, what essentially we have is the C1 will have, so we have in the first case C0 having a greater concentration than C1. In the second case, we have our C1 which have our greater concentration than that of C0. In the same frames of reference, we have now introduced the second case wherein the C1, this case here, we have the C1 that has a greater concentration than C0. Now the flux will be in this direction. Since there is a negative, there is a change, the flux is now in the opposite direction. The negative that appears here when we use the Fick's first law makes sense, because in the same framework we have a flux in the different direction. So what essentially we have seen is, from just by considering the magnitude alone, we are able to now justify what, or we are able to, just from a mathematical perspective alone, we are now able to rather understand what Fick's first law states. So what essentially it states is, you have a flux in an heterogeneous system, and this essentially depends on the magnitude of it, essentially depends on the slope that rather quantifies the difference in the concentration. You have a heterogeneous system. In that system, the concentration varies with space, and when you have such a system wherein the concentration varies with space, there is going to be a flux that is introduced. The direction of this flux depends on the partial derivative of the concentration with respect to the spatial coordinates. And when you, there are two possibilities, there are two conditions that are possible, and when you consider, when you fix a convention with this condition here, then when this condition is satisfied, that is the original concentration, the initial point, the concentration at the initial point is greater than the concentration at the subsequent point, then you would have a flux, then you would have a positive flux. You fix a condition that in this direction we have a positive flux. When you fix a convention that in this direction you would have a positive flux, then you would have a flux when the concentration is moving from, or when you when you progress and the concentration changes from a higher concentration to that of a lower concentration. On the other hand, when the condition switches back and the initial stage or the initial point the concentration is lower and the subsequent point is concentration is higher, there will be a negative flux, and the direction of this flux is being captured by the sign, the negative sign here. So what essentially this negative sign captures the direction of the flux. So what essentially we have is, what essentially the Fick's law states is, the Fick's law, it captures the direction of the flux and also the magnitude of the flux, and the way it captures is by considering the magnitude comes from the partial derivative of your concentration. This is what governs your magnitude, and by convention we have the negative sign here, and it indicates that the flux from the higher concentration to that of the lower concentration will be positive. So you have a positive flux in a specific direction for a specific system, and that flux will be from the higher concentration to that of the lower concentration. Now, this direction is again for a simplistic case. We have considered a simplistic case, and this direction it stems from the convention. So when you have such a consideration, so when we have considered our system to be in this way, when we started off with this condition, and the flux, the corresponding flux we refer to as the positive flux, and if the system in itself is reversed, we end up with this reverse, so with this opposite flux. So only those two concentrations are possible, or those two directions are possible through this convention here. However, the gradient does more than that. So we have seen that gradient, so the way the gradient is represented is by the nebula here. So this is the way the gradient is represented. So gradient of this function, the concentration in an heterogeneous system, is again, it comprises of the partial derivative and includes a directional component to it. So what essentially we have is, when you consider a gradient of a function, what you end up having is, this is a vector. So a gradient of a function will give you a vector. Now this gradient, we are able to understand the magnitude of this vector here. So the partial derivative of respect to x, with respect to y, and with respect to z, and the summation, or these individual components, these all contributes to the magnitude of the vector. How would we understand the resulting direction of this vector? Because when we say that gradient of a concentration is a vector, then in that case the gradient needs to have both a magnitude and a direction. Now the magnitude, again, it stems from the partial derivative. However, we are not so sure about direction. In which direction is this gradient of concentration pointing at? It is something that we need to understand, because the Fick's first law, it not only considers the conventional sign here, but it also considers the gradient of the concentration. It means there is a direction associated, there is a direction around which this particular vector is pointing. So we need to know, to have a complete understanding of what the Fick's first law is, we need to know what is the direction, the resulting direction of this vector. Now the reason I have represented J in this manner is because usually when you know that, when you see a consistent book and when you consider the Fick's first law, then since we are considering the gradient of the concentration, and the gradient of concentration is a vector, the flux is also a vector. So the flux is a vector, and therefore it needs to be differentiated from just J, which is the magnitude of the flux. So in order to differentiate it, some textbooks might use bold J, or some textbook might use an arrow over it. So ultimately this flux has a specific direction associated with it, and that direction comes from the gradient of the concentration. Now we need to know what is the gradient of this concentration. Now generally when we want to find what, when you say we have a frame, say for instance I have a frame of reference, unit directions u cap, and I want to find what is the direction of this given vector with respect to this unit vector u cap. So I want to know what is the direction of this vector, say c vector, with respect to this unit vector. So if I want to do that, what I essentially need to do is, if I am able to estimate what this theta is, then essentially with respect to u cap, with respect to this unit vector, I will be able to say how this particular vector is rather inclined. So when I am able to introduce a unit vector and then we find the angle between the unit vector and my actual vector, then I will be able to describe the direction of this vector. So what essentially it means is, so the gradient of C is a vector, and if I want to find the direction of this vector, then I can do it by introducing a frame of reference, a unit vector, and if I find the angle of inclination between this unit vector and this vector, then I will be able to describe its direction. Now how can I find the angle of inclination? Now it is possible for us to consider the dot product of these two vectors. The dot product is nothing but we are projecting this onto this, so essentially not subtracting, we are just projecting it onto this. This is one of the meaning for it. Or the dot product also increases, or it introduces the the angle of inclination, so we can consider that as well. So when you do that, so the gradient of C and the dot product of this unit vector, say this unit vector can be I vector plus j vector plus k vector, it's just a unit vector. So you have your unit vector and you have your gradient of C. So what it essentially means is the dot product of these two, what it essentially means is that we have considered the magnitude of the gradient alone, the magnitude of the unit vector, and the angle between them, cos theta. So since this is a unit vector, the magnitude of this vector is going to be 1. So we have our gradient magnitude of the gradient vector and cos theta. So what essentially then I can do is, I can estimate the cos theta by considering from this expression here. So what essentially we are doing is, in order to find the direction, we are introducing another unit vector and we are finding the direction of the given vector with respect to that of the other unit vector. So with reference to the unit vector, we are finding the direction of our gradient C. So this is one approach that we can adopt. Now my question is, I want to know along which direction is my C pointing at. So if you could recollect, we can extend this expression here, and since this is a unit vector, so this u is a unit vector, if I add to this expression here, that is the norm of gradient C cos theta, and if I add the unit vector here, again this is a unit vector, so it is not going to change the magnitude, but I'm just adding it here. So I'm just augmenting it here. So what essentially it means, so this again is a scalar value, and this is the unit vector with just a direction, and it points in this direction. So what essentially this would be a vector, and this vector will be pointing along the u direction. Okay, and it will be pointing along the u direction, and the magnitude of that vector will be this. So the norm of nebula C cos theta will be the magnitude of the vector that is pointing along the u direction. So I have projected the C vector onto the u vector, thereby I have calculated the magnitude of it, and I have just included the u vector. So this is a scalar, and this comprises of the magnitude of this dot product, and I am multiplying it with a unit vector. So what it essentially means is how much of the C vector is pointing along the u direction is what we have here. So this combination of these two will yield me a vector. So what essentially now I have done is, I have introduced a unit vector, and I have found out what is the magnitude of the gradient C acting in this unit vector along the unit vector direction. Now if I replace this with delta C, with the gradient C, what do we have? So if I replace the unit vector with the direction of the gradient C, if I replace this unit vector with the direction of the gradient C, what it means is, so it means the gradient C, and it is the ratio of the gradient C and the norm of gradient C. So this will give me a unit vector that is rather along the direction of the gradient C. So I have a gradient C vector, and this gradient C vector is pointing in this direction. What I am doing is, I am considering both the magnitude and direction of this vector and dividing it just by the magnitude, and this gives me a unit vector u cap. So this gives me a unit vector u cap. Now what then I can do is, I can substitute this u cap. I can find the dot product of the gradient C and the u cap. So this is my u cap, and this is a vector for which I need to find the direction. So when I consider the dot product, what essentially would happen is the theta would become 0, and then what essentially then we would have is we would have the dot product of these two values, and just the dot product will get multiplied. So when I multiply these both together, then I have C and norm of C. So what essentially then would happen is these, so we will have two norms. The square will appear because we are multiplying this with this, and we are considering the dot product. So we will have two norms in the numerator and one norm in the denominator, and these two get cancelled out. So ultimately this dot product will yield me the norm of the gradient C. So when u cap is pointing, the unit vector is pointing along the direction of the gradient vector, I get this value. Okay. If it is not pointing along the gradient vector, then I get this value. So there are two possibilities. The u cap, the unit vector that gives direction to my gradient. So the u cap, it gives the direction to my gradient. It can align itself along the direction of the gradient, or it can align itself away from the direction of the gradient. Then it aligns itself along the direction of the gradient. So there are two possibilities when you take this dot product. So one, it can align itself in the direction of the gradient, that is theta will be 0, or it will be theta not equal to 0. If the theta is 0, then the dot product will yield me the norm of the gradient of concentration. If it is not equal to 0, then I will end up having this expression here. Now, given the values of theta we know, this term here will always be less than that of this term here. So what we mean is the dot product will assume a greatest value, the maximum value, when the unit vector is along the direction of the gradient of concentration. So the maximum value is when the unit vector is along the direction of the gradient vector. So then what is the way we can describe then the unit vector that dictates the direction of the gradient vector is the direction of the gradient vector C, or the gradient of C is the one where we have maximum magnitude. So this inference we can make from this relation here. Now, to pull it all together, when you consider an heterogeneous system, the concentration is spatially varying. So that can be translated into a function. And it is possible for us to take the gradient of the function. So gradient of the function is nothing but the derivative of the concentration with respect to each of the spatial coordinates. And to that you introduce the vector notation. So you have the derivation or the partial derivative of concentration with respect to x, one of the spatial coordinates related to I vector. The partial derivative of c with respect to y related to j, partial derivative of c with respect to z related to k vector. So ultimately you have a gradient of concentration that is a vector. Now we want to find the direction of this gradient. So we want to find, now to find that we introduced another unit vector. So there are two possibilities for this unit vector. This unit vector can lie along the direction of the gradient, or it can lie in any other direction. So if it lies along the gradient of your concentration, then the magnitude of the gradient will be the maximum. If not, the magnitude will decrease. So in order to ensure that, in order to rather identify the direction of the gradient, we introduce a unit vector u, and the characteristic feature of this unit vector is if this unit vector is along the gradient of c, then the magnitude is maximum. If not, the magnitude of the gradient c is rather diminished. So the magnitude of the gradient c is maximum when the unit vector is aligned along the gradient of c. If not, the magnitude of the gradient c is minimized. So therefore, the direction of the unit vector or the direction of the unit vector, it coincides with the direction of the gradient c when the magnitude is maximum. So from that we can state that the gradient c, the vector gradient c, is pointing in the direction of maximum magnitude. So you introduce a unit vector and the unit vector will lie along. So this you have the gradient c vector and you have a unit vector. When these lie along the same direction, the magnitude is maximum. The magnitude would be the norm of gradient c. And in this case, when you have such a case, it means that both the unit vector and the gradient c vector are along the same direction. So one other way of putting it is the gradient vector is along the direction of the unit vectors, and this unit vector is characterized by the maximum gradient direction. So therefore ultimately the gradient vector will point in a direction where the slope is maximum. So where the magnitude of the vector is maximum, wherein the summation of the partial derivative is maximum, in that direction your gradient will point. So when you consider a gradient, supposing you, so if you consider just how it works, if you have your point here and the next point is this, and so you have consider a three-dimensional representation. The next point is this one, the next point is this one, the next point is this one, the next point is this one. So essentially, depending on where the gradient points, the direction of the gradient is, it depends on the largeness of the slope. The gradient, it points towards the direction. So the gradient, it points towards the direction of the largest slope. So we are able to, so in the Fick's first law we have this gradient term, and now we are able to understand what the magnitude of the gradient means. So it's just the slope, the summation of the slope with respect to the spatial position, and now we are also able to see what the direction of this gradient is, and correspondingly your flux will flow. Your flux will flow, the direction of your flux will be in the direction of your maximum slope, the largest slope. So the positive and negative direction, the positive and negative components, it comes from the convention. So we fix a convention and the positive and negative comes from that convention. But when we have several points that satisfies the convention, then the direction in which the flux flows is the one with the largest slope. When you have a specific combination of points wherein the disparity, the difference in the concentration is the highest, then along this direction alone the flux will begin to flow. The amount of flux in that direction will be, the flux in that direction will be higher. The amount of transport of mass in that direction will be higher. So we will build on this in the subsequent lecture. Goodbye.